All right, folks, let's go ahead and get started. So we're starting with our first colloquium of the spring series by our very own Simon Foreman, here, in case you haven't met him yet. Simon's research, as he'll be telling us a little bit about today, involves the potential for cosmological measurements to provide insights into the fundamental constituents of nature. So he does work in a broad range of physics, including theory, simulations, and data analysis. And as we'll talk about today, he has a particular interest in the 21 centimeter intensity mapping. But he's also worked on gravitational lensing, cosmic microwave background, and effective field theory-based approaches to cosmological perturbation theory. So Simon got his PhD from Stanford back in 2016. After that, he had postdoctoral fellowships at the Canadian Institute for Theoretical Astrophysics, the Perimeter Institute for Theoretical Physics, and at MIT. And then he came to join us here. I believe you've been here about 1 year now.
That's right. Yeah, 1 year.
So after 1 year, we welcome Simon to give a colloquium, and especially I think we'll graduate student faces in the audience, which I think we're all very happy about, and if they're interested as well, because Simon is still a relatively new faculty member, he is indeed looking for students. So hopefully we will all get to hear an exciting talk by him today. All right, go for it.
Great. Thanks very much.
Two doors down from the mic, and he appreciates when it is too cold. In addition to a good physicist, he's
Canadian, so I like it cold. All right, so thanks very much, Cindy, for the nice introduction, and thanks everyone for coming. I'm going to tell you today about the relatively new field of 21 centimeter intensity mapping, a subfield of cosmology. And so I'll tell you what this technique is, why it's exciting, and what kind of things we could potentially learn from it. So a little more detail of what I'll say. I'll start off by reviewing some of the major open problems in cosmology that are spurring a lot of theoretical and observational work in the field. And I'll connect these open problems to the topic of cosmic large-scale structure, which is the overall distribution of matter in the universe. From there, I'll segue into the main focus of the talk, which is the technique of 21 centimeter intensity mapping. I'll motivate why this is a promising technique to map the cosmic large-scale structure. I'll tell you what it actually is, and I'll go over some recent results from the CHIME telescope, which is a project that I'm heavily involved in. And then the last part of the talk, I'll give you a mini roadmap towards some things which will be coming down the pipe in the next few years, and specifically things that we're working on here at ASU. So to set the stage, we can think of our current picture of cosmic history. The most important zeroth order fact that we know about the universe is that it is expanding. So if we think about the universe today and we wind the clock back, as we wind the clock back, on average, the universe is getting hotter and denser, and the average energy in the universe is increasing. If we wind the clock back far enough, eventually we reach an epoch where the universe is so hot and so dense, which where at this time all of our standard physics descriptions begin to break down, and we label this time as the Big Bang. Now, if we start at the Big Bang and we run the clock forward, the essential story of the evolution of the universe is the story of things sticking together and of structures growing. And based on what we understand about physics since the Big Bang, we can pick out a number of important milestones in the history of the universe, mostly related to things sticking together and things growing. So about 3 minutes after the Big Bang, based on what we understand of nuclear physics, we know that the free neutrons and protons which were in the universe could first bind into the lightest stable nuclei, things like hydrogen and helium and lithium. If we run the clock a bit farther forward, there are still free protons and electrons in the universe, but about 400,000 years after the Big Bang, the universe is cool enough that these free protons and electrons can mostly join together into neutral hydrogen atoms. At this point, the dominant interaction between photons and particles, that is Compton scattering, shuts off, and the radiation density of the universe, that is the perturbations in the radiation density, remain essentially fixed from this epoch through to the present day. And we can observe these fluctuations as the cosmic microwave background, which you might have heard of, and we get a tremendous amount of information about cosmology from this probe. Winding the clock farther forward, eventually the first primordial clouds of gas can condense within gravitational potentials and form the first stars. Around the same epoch, we start getting the formation of the first early galaxies, and then these galaxies tend to clump together and form the wider structures that we see around us in the universe. And so in the end, we have a variety of structures that we can observe around 13.8 billion years after the Big Bang. And so this is the time at which we sit and the time at which we try to make observations to learn about this entire cosmic history. Now, the nice thing about these specific milestones that I've written on this slide is that for the most part, they can be described with physics which is entirely known. So by the time you finish your undergraduate physics degree from ASU, you already have the vast majority of the physics knowledge that you need to describe all of these important milestones in the history of the universe. So things like general relativity, statistical mechanics, and the particles and interactions of the Standard Model. Maybe you'll need to do a bit of extra reading about general relativity and particle physics if you're just finishing up your ASU physics degree, but by and large, you already have the core knowledge that you need to describe a lot of the story of the universe's history. However, if we broaden our perspective a bit and we really want to understand all of the richness of behavior that's going on in this picture from early times to late times and at all the regimes that are interesting, then we need a little bit more than known physics. There are actually a lot of mysteries within this picture. That is, observations tell us that there are physical ingredients which are missing from the standard physics that we know. And it's a main objective of observational and theoretical cosmology to try and identify the ingredients that are missing and pin down their precise theoretical descriptions so that we have a full description of the universe and we can connect this to our knowledge of fundamental physics. Now, let me move on to review three of the main mysteries that we have in our picture of the universe as it stands. So the first mystery concerns the extreme early epochs of the universe. The leading theoretical scenario for what happens in the first few moments after the Big Bang is that the universe begins with a short period of exponential expansion. So for most of the universe's history, we expect that its size has expanded with time like a power law in time. However, what we postulate at very early times is that instead there was an expansion which went like an exponential of the time. Now, if we make the simple postulate that there's early exponential expansion of the universe, then this ends up naturally explaining a lot of the properties that we currently observe for the present day universe. These are things like homogeneity, the fact that on average, the properties of the universe look the same if we consider it in different spatial locations. Also, flatness or lack of curvature in a general relativistic sense. Also, the fact that we don't observe any magnetic monopoles, so the density of magnetic monopoles must be very low. All of these things naturally come out as consequences of an earlier period of exponential expansion that's called cosmic inflation. Now, we can ask what might cause this exponential expansion, and we're naturally driven to an explanation that it must be some quantum fields which are not part of the Standard Model. With a potential caveat that there are some proposals that the Higgs field might be able to drive this exponential expansion, but you need to postulate some special properties of the Higgs. So the more favored explanation is actually there's something missing from the Standard Model, some new field which has a potential energy which can couple to gravity and drive this expansion. Now, this is not the whole story of cosmic inflation. Actually, if we assume there's some other new fields that are active in the early universe, then we get another ingredient for free. And the ingredient is actually the fact that the universe has structure in it at all. If we postulate that there's a quantum field active at this early time, then the quantum fluctuations in that field get effectively blown up or amplified by inflation. And these quantum fluctuations act as seeds for the perturbations in the distributions of radiation and matter that we observe in later times. So these will seed, for example, regions of the universe with a density which is slightly higher than average, and then gravity does its job. It pulls more matter in to create deeper potential wells, and eventually bound structures form, and then they form the web of structures that we see today. So cosmic inflation, in a sense, it's a nice package to explain a bunch of properties of the universe, which are otherwise unexplained. However, inflation creates new problems of its own. We said there's something missing from our understanding of physics, but we don't quite know what it is. We haven't yet pinned down the precise identity of these fields, which are hanging around in the early universe. We don't know how they interact, and we don't know whether they might be related to other topics in high energy physics, such as axions or string theory. There are certainly proposals along these lines, but we don't have enough observational input to pin down the single correct answer. And so what we need is more observations and also more work on the theory side to try and enumerate the space of potential solutions and try and rule these solutions out one by one until we're left with the unique correct answer. Now, there's a second mystery, which happens at the opposite end of the history of the universe, the more recent end. And this mystery goes by the name of dark energy. Dark energy is the name given to the fact that the expansion of the universe has been accelerating for roughly the past 4 billion years. Prior to this time, the expansion of the universe was actually slowing down. You can think of this as the gravitational pull of all the matter in the universe acting to counteract the inertia, which came from its initial expansion. However, about 4 billion years ago, there was a sign change in the rate of this expansion, and it stopped slowing down and began speeding up. And we still don't quite know the physical explanation for why the universe's expansion is speeding up, and the name given to this is dark energy. There are a few possibilities for this. This could be a pure cosmological constant, an extra term in Einstein's equations, which we're allowed to write down. There could be some dynamical reason, which is driving the acceleration, such as some extra scalar field, similar to the scalar fields which might be driving inflation. Or it could be true that we just don't understand how gravity works at cosmological scales. And if we understood the correct modification of GR, then perhaps this acceleration would naturally fall out as a consequence. Different people in the field have their different favorite possibilities amongst this list, but we haven't quite pinned down which one, if any, is correct. And so again, we need more observational input into this question. The third major mystery is dark matter. We have several lines of evidence that tell us that around 85% of the universe's matter only interacts gravitationally. So it cannot be particles that are members of the standard model. It needs to be something else which doesn't interact in the way that normal matter does. One of the classic demonstrations of the existence of dark matter is shown in this diagram of the bullet cluster, a particularly special cluster of galaxies, which has been observed in various wavelengths. And different types of observations of the bullet cluster are color-coded into different colors in this diagram. The pink regions correspond to X-ray emission, which comes from hot gas in the neighborhood of this cluster, where the bluer region corresponds to the total amount of matter in this neighborhood as determined by gravitational lensing. The effect of gravitational lensing is to bend rays of light which pass by particularly massive sources. And so by examining the images of the galaxies which sit behind this cluster and looking at distortions in these images, we can make an inference about the total amount of mass which sits in the foreground. And when you run this procedure through, you find that there must be some large amount of mass which is concentrated at a spatially distinct location from where the hot gas is sitting. This tells us that there's some matter which is not emitting like we expect normal matter to, but it nevertheless has a gravitational influence on the surroundings. And this is what we call dark matter. So this is a fairly local piece of evidence for dark matter. You can go even more local and look at rotation curves of galaxies, or you can go to much larger scales and think about the overall evolution of the universe and the evolution of structures on average. And there's also evidence in this regime that points to the existence of dark matter. However, this solution to one problem creates problems of its own. We still don't quite know what the dark matter is. It's possible that it's a single particle which interacts fairly weakly with the other particles that we know. It's possible that it's a particle of much lighter mass, such as an axion. Or it's possible that there might not be one dark matter particle. There might be a whole rich dark sector. So you could think of a whole family of particles, maybe dark protons, dark atoms interacting with dark photons, none of which interact with the standard model, but which all interact with each other. And again, we don't quite know which one of these options, if any, is the correct one. And so there's more work done to try to figure out what these different models of dark matter might do in observations, and then go out and make the observations to try and get some constraints. And there are other open questions in cosmology, certainly, that I haven't focused on, but in my mind, these are the big three which connect to fundamental physics and are amenable to observational tests. Now we can ask how we might get some insight into the solutions for these mysteries. And they share a common theme. The common theme is that various proposals or theoretical models to explain each one of these mysteries tend to have unique imprints on the large-scale structure of the universe. This is the name we give to the distribution of all the stuff in the universe. So all the dark matter, all of the gas and stars and other massive objects which make up the universe. There is a pattern of clustering or different patterns of clustering that we can observe when we make big maps of this structure. And by looking at this structure in different regimes, we can hope to pin down some of the answers to these main problems. And so we can zoom in and try and ask what kinds of things we're looking for in the large scale structure to learn about these different open mysteries. Starting with the early universe, there's a nice connection that you can make between endpoint correlation functions of large scale structure and the properties of the quantum fields which might have driven inflation. So you can think about a two-point correlation function of large scale structure. Easiest way to think about this is the correlation function of galaxy positions. So for example, you could take some pair of random galaxies and ask, how likely is it for those galaxies to be a certain distance apart? This is a version of a two-point correlation function. You could also take a random triplet of galaxies and say, how likely is it for these galaxies to be in a certain triangular configuration with a certain opening angle or side lengths? And you can also make analogous quantities just by looking at the distribution of mass or the distribution of dark matter, but the galaxies are a little easier to think about. And it turns out that you can draw a precise connection between observations of endpoint correlation functions and interactions or other properties of the quantum fields which drove inflation. So for example, if you write down the Lagrangian of some field which might have generated inflation, for certain classes of models, you can map cubic terms in that Lagrangian into signatures in the three-point function. This is similar to the way at colliders we collide particles in order to learn about interactions with particles. And this is why this procedure is sometimes called cosmological collider physics. We're not colliding particles, but we're looking at density correlations at endpoints, and this is telling us about the particles or the fields which cause those correlations in the early universe. Now we can also look to large-scale structure to learn about dark energy, and we can do so by looking for a standard ruler in the distribution of matter. A standard ruler is a quantity for which the physical size has been calibrated using some other observation, and then by observing this ruler, observing the angular size of this ruler, we can figure out how far away it is. So you can think of viewing a car which is moving towards you. You know roughly how big a car is. If you see this car and it's taking up your entire field of view, then you should move out of the way because you'll probably get run over. On the other hand, if you see this car and it looks extremely tiny to you, then your brain automatically does the calculation to say, oh, that car is far off in the distance. In cosmology, our car is actually a certain length scale that we can predict the physical length of in the clustering of matter. This is related to the distance that sound waves can propagate between the beginning of the universe and so-called cosmic recombination, when these sound waves tend to stall out after the photon baryon fluid decouples between the photons and the baryons. What we look for in cosmology for a standard ruler is a certain excess of correlations in large-scale structure at a certain distance. In effect, we expect galaxies, pairs of galaxies, to have a preferred separation that is just slightly preferred above the mean. And by measuring large-scale structure in different ways, by looking for this standard ruler at different redshifts or different distances away from us, we can try to map out the effective size of the universe and see what the universe's acceleration looked like, and then try and learn something about dark energy in this way. Finally, for dark matter, there are different ways to go to try and constrain it. One of the interesting ways is to look at the abundance and properties of small-scale structures. So by looking at the clumps of dark matter, which host individual galaxies, or perhaps clusters of galaxies or other structures like this, we can try and constrain the properties of the dark matter model. For example, its temperature, whether it interacts with itself strongly or interacts with anything else in an observational way, in an observationally constrainable way. So overall, there's a lot of motivation to go out and try and make big maps of where everything is in the universe, and then drill down into the details of these maps and try and learn something about these different theoretical scenarios. So how do we want to map the large-scale structure of the universe? Well, thus far, the most successful way to do so has been with a large spectroscopic galaxy survey. The way this kind of survey works, in a nutshell, is that you start by taking imaging of large regions of the sky. You look at these images and you try to identify the angular locations of individual galaxies within these images. And then you take a spectrograph, you point it at each galaxy, and you measure the spectrum of the galaxy. Based on the type of the galaxy, we expect the spectrum to have certain features, mostly emission or absorption lines from various chemical species. So we can observe where those lines fall in the spectrum and see if they're shifted with respect to where we expect them to be. If they are shifted, we can associate this with a redshift of the galaxy spectrum, and then use our knowledge of cosmic expansion to relate this redshift into a distance, how far the galaxy is away from us. So in this way, we can build up a three-dimensional view of where all the galaxies are, the angular positions coming from the images and the line of sight positions coming from the redshifts. And so this has been going on for several decades now, and it's been extremely successful. Here is a brief animation showing a compilation of 20 years of data taken by the Sloan telescope, which ran in New Mexico. And it's still operational, but is now looking for other things. And so as we zoom in on this compilation of data from the Sloan telescope, and remember that each point in this diagram represents a galaxy whose position has been measured, we can see if you squint in this light, you still should be able to see the tremendous amount of structure which is revealed as we zoom in particularly to the green region on where all these galaxies are located. And again, by looking at the statistics of the distribution of these galaxies in different regimes, we can learn quite a bit about cosmology. For astronomers or astrophysicists who are also interested in the properties of these objects themselves, this is also a bonanza of data to study different populations of galaxies and how these populations grow and merge and behave. So essentially, the main way that large-scale structure has been mapped so far is to try and count galaxies one by one, and then look at where they are and study the features of their clustering. However, when we think about this technique, there are a few natural questions which might lead us to alternative ways to map large-scale structure. These are questions such as, what about the dimmer objects? For a given telescope and a given survey speed, you can only individually identify galaxies which are sufficiently bright. There might be dimmer ones nearby whose clustering information we want to make use of, but we can't pick out one by one, and so we can't add them to our catalog. Also, what about the earlier universe? As we want to clock back, there just aren't that many galaxies around to map large-scale structure. Or maybe even earlier, there are no galaxies around, but there's still dark matter and gas, which has clustering patterns, which we want to make use of. And so we might ask whether there's a different technique which we can use to harness the clustering information at these earlier times. And finally, we might ask, just for the sake of complementarity, whether there's an alternative way that we can map the universe. This point of complementarity has become particularly important in recent years in cosmology, thanks to something known as the Hubble tension. So the Hubble tension is a current discrepancy in observations of the current expansion rate of the universe, measured in many different ways. And the statistical precision of this discrepancy has reached at least 5 sigma, depending on which analysis you look at. So there's a significant difference in measurements that we have tried to make of the same quantity. Now, to solve this discrepancy, it could be true that one or more of these measurements has some error in their analysis, or it could be that the theory that tells us these measurements should agree is wrong, and we need a new theory to try and reconcile the observations with what we believe. No matter what the solution is, we're going to learn quite a bit because we tried to measure the same quantity different ways. And so we can extrapolate this procedure or extrapolate this logic to large-scale structure and say, if we're trying to learn anything interesting about the distribution of matter, we would be well advised to try and learn this thing in more than one way, both to check that it agrees, to make sure that there are different systematics in our different measurements so that we're not getting confused by systematics. And if these different measurements agree, then in principle, we can combine them all into a bigger Uber analysis and learn even more about the universe in this way. So we're motivated to ask whether these galaxy surveys might be the only game in town or whether there's anything else we can do. And it turns out there are a few different options for other things we can do, and I'll focus on one in particular in this talk. And we can think about this by starting with the standard galaxy survey that I described. So in a given survey, there will be several objects in a patch of sky which are bright enough to identify one by one. And there might be many more dimmer objects visualized by the gray dots here, which we can't identify one by one, but which are out there and whose clustering information we want to use. To figure out how to harness the information of these dimmer objects, we can appeal to our knowledge of quantum mechanics, and in particular, our knowledge of the hydrogen atom. We know that the hydrogen atom in its ground state possesses a hyperfine splitting between the state where the spins of the proton and the electron are aligned or anti-aligned. If these relative spins flip from aligned to anti-aligned, then the atom transitions to a slightly lower energy state and it emits a photon with a wavelength 21 centimeters, an important number you might remember from the title of this talk, or a frequency about 1.4 gigahertz. what we know is that at a sufficiently late time in the universe's evolution, the vast majority of neutral hydrogen gas that contains these hydrogen atoms is locked inside galaxies. And we know that these galaxies are all going to be emitting with wavelength 21 centimeters. For an individual hydrogen atom, the spontaneous transition is extremely rare. However, this is compensated by the huge abundance of hydrogen atoms out there in all these galaxies. So if in principle we had a telescope that could just make a map at 1.4 gigahertz of all of the emission coming from the sky at this wavelength, then we expect that the main thing we would be measuring would be the 21 centimeter emission from all of these galaxies, both the brighter galaxies and also the fainter galaxies. All of that information would be covered in this map. And then we wouldn't need to count the galaxies one by one. We would just be able to look at this gap and say, this map and say, oh, there's a bright spot here. There must have been more galaxies in that spot, and there's a dim spot, and there might not have been so many galaxies. Now, this is a demonstration of a two-dimensional map of this 21 centimeter emission. We can actually do a bit better than two-dimensional maps, using, again, the fact that we know the universe is expanding. So we know that objects farther away are emitting radiation, which we will measure as being redshifted by a greater and greater amount, depending on how far away these objects are. And so instead of making one map at 1.4 gigahertz, we can actually make a whole stack of maps where each map is made at a slightly different observing frequency, corresponding to some frequency slightly lower than 1.4 gigahertz. And then we can look at the fluctuations of one of these maps and realize that these fluctuations are telling us about the galaxies which are located at a distance which is slightly farther away because their emission has been redshifted slightly more. We can take these maps and stack them up and then build up a 3D map of the universe where the distance axis now maps into the observing frequency of our maps, and then the angular axis is just the angular direction of the map. And so this is an alternative way, and in principle, a much faster way to capture the information in all of these faint galaxies rather than trying to find them one by one. Basically, in one shot, we just make a big map, and then we got all of this information. And if we can understand the properties of these maps, then we can harness that information. And so coming back to our three questions about how to do something different from a galaxy survey, we see this strategy of intensity mapping provides a natural answer. The maps that we make will contain the information from both the bright and the dim objects. They'll contain radiation from gas which is inside galaxies, and also any gas which is outside the galaxies. So at an early time when there's no galaxies, but there's still gas, we can still make these maps and learn about its clustering. And these maps will be at very different wavelengths than what we use for optical galaxy surveys. So the systematics and the observing strategies will all be very different. So we're satisfying our desired property of complementarity as well. Now, how do we want to do this in practice? Well, we want to make sky maps at 1.4 gigahertz or lower. This is firmly in the radio part of the electromagnetic spectrum. So we need a radio telescope. And radio astronomers have been building these telescopes for a long time. And so there's already many facilities which could in principle be used for 21 centimeter intensity mapping. So these include the Green Bank telescope in West Virginia, the Parkes telescope in Australia, and the GMRT array of dishes in India. Now, all of these facilities have been used or are being used for 21 centimeter intensity mapping. And in fact, some of the first detections of the intensity mapping signal came from Green Bank and Parkes. But when people started thinking about how to really maximize the utility of this technique a few decades ago, they quickly realized that these existing facilities are not quite optimal. What we really want is a custom-built telescope designed to have the sensitivity that we need to do systematics mitigation properly and map the right spatial scales and the right angular scales and have an efficient enough mapping speed that we can actually make the low noise maps we need in order to play this game and learn about cosmology. And so at the same time, some of these instruments were starting to gear up their own 21 centimeter intensity mapping efforts. There were other groups thinking about how to build cost-effectively custom telescopes to try and do the same task. And so there are several facilities now which exist or are currently under construction, which are trying to do this. The facility which is farthest along in this effort is also the facility that I'm heavily involved in. And this facility is called the Canadian Hydrogen Intensity Mapping Experiment, or CHIME for short. This is a radio telescope and radio waves have long wavelengths, so radio telescopes need to be big, and this is why CHIME is a big telescope. It's composed of these 4 parabolic cylindrical reflectors, each of which are 100 meters long by 20 meters wide, and which are all oriented in the north-south direction. If you wait a second, you can see the person who is flying the drone appearing there, so that gives you a sense of scale of this telescope. Now, CHIME is so big that it is designed not to move around to try and look at different regions on the sky. Instead, CHIME takes a lazy approach. It just sits motionless on the ground, and it waits for different portions of the sky to drift overhead and pass through its main beam. So in this way, the telescope can make a map of the entire northern sky every night. Now, we don't make a map directly. In fact, what we do is use the principles of radio interferometry to try and post-process our data into maps. In detail, what we measure is the electric field located at the positions of each of 1,024 radio antennas, which are suspended upside down from each one of these focal lines. And what we save is the correlation between the electric field measured at each antenna with each other antenna in the array. So we save all of the pairwise correlations. What we can realize using interferometry is that the correlation between 2 antennas, which are separated by a given distance, tells us about a given Fourier mode of radiation that we measure on the sky. And so by measuring enough of these Fourier modes, we can gather them together and do an inverse Fourier transform and then reconstruct a map of the intensity and polarization of the radiation on the sky. And so we do this after the fact. And this observing strategy also allows us to do a lot of systematics checks and mitigation that we wouldn't be able to do otherwise. So this is how the telescope works. In a nutshell, it's been operating at full speed for over 5 years, and we save roughly 1 terabyte of data to disk per day. This means we have well over a petabyte of data on disk, and we're currently analyzing this in different ways to learn about cosmology and also other topics in radio astronomy, which I won't touch on in this talk. CHIME was originally proposed and constructed by a group of 3 Canadian universities, as well as the Dominion Radio Astrophysical Observatory, which is a nationally funded radio astronomy facility in Canada. And since the creation of CHIME, various other universities have joined with partners. Myself and my group here at ASU represents the contribution to ASU. And there are a few others in the US and Canada and China. Importantly, the CHIME collaboration acknowledges that CHIME is located on the traditional, ancestral, and unceded territory of the Syilx Okanagan people, and we're grateful for the opportunity to perform research on these lands. Now, CHIME was designed for a specific purpose, and this specific purpose is to learn about dark energy. Here's a forecast plot, which gives you an idea about what CHIME could measure in a statistical sense. So on the x-axis here is redshift. This is a proxy for how long ago in the universe's history we are measuring. On the y-axis, or I should say these points are telling you the size of the relative error bars that we can obtain on a specific measure of the effective size of the universe or the cosmic expansion history as a function of redshift. The ideal case scenario for CHIME is shown in orange, and we can compare this with other forecasts for DESI, which is a state-of-the-art spectroscopic galaxy survey, which follows the technique I talked about a little while ago, and which is currently taking data at a telescope in Kitt Peak right here in Arizona. DESI is expected to be one of the state-of-the-art surveys for the next few years, which is going to measure the properties of dark energy. But we can see based on this forecast, we expect comparable statistical precision of CHIME compared to DESI from a telescope which was much cheaper to build and which has a much smaller team which is running it and analyzing its data. Now, just for perspective, these error bars directly map into error bars on the expansion of the universe at different times. And this redshift range was tuned to match the range when this dark energy, this accelerated expansion, is just turning on. So hopefully by mapping the transition from non-dominant dark energy to dominant dark energy, we can start to learn a lot about what's going on here and hopefully learn something about dark energy. Now, however, you'll notice these orange error bars have a long and carefully worded caption, and that has an important reason. These error bars assume 1 year of clean integration time on CHIME, assuming no foregrounds and no systematics. So assuming that we're in the purely statistics limited regime of these measurements of dark energy. This is a large caveat. In fact, with the data set we've taken already, we are not in the statistics limited regime, we're only in the systematics limited regime. So all of our effort right now is on pinning down various systematics in the data in order to make good on this promise of extreme statistical precision. So why is this so hard? Well, I can show you an example of a simulation which puts that into a bit more clarity. Here is a simulation of the intensity of radiation that we might observe along a single sight line in the sky with CHIME as a function of observing frequency, which again maps into line of sight distance for the 21 centimeter signal. This jagged black line shows you a simulation of the cosmological signal that we're after, whereas the other colored lines show you simulations of a variety of astrophysical foregrounds, which we also measure within the same observing frequencies. These are dominated by synchrotron emission from electrons spiraling around magnetic field lines in the Milky Way, as well as other various sources, for example, radio point sources, either inside the galaxy or outside the galaxy, and other kinds of emission which might come in a diffuse way. If you look to the left of this plot, you'll find that it's on a log scale. And so what you realize is that collectively, these contaminating foregrounds are 4 to 5-ish orders of magnitude larger than the signal we want. And so this is the challenge we face, and this is why this hasn't been done already, essentially. There's an extreme difficulty in trying to pull out a signal which is buried under 5 orders of magnitude of contaminants in our data. The scientific potential is huge, but the challenge is also quite steep. Now, the thing which could potentially save us is the fact that the physics of the foregrounds dictates that they should be very spectrally smooth. That is, as a function of frequency, they shouldn't vary that much, whereas the 21 centimeter signal is expected to vary a lot. So if we can separate smooth spectrum foregrounds from non-smooth spectrum 21 centimeter emission, then our job will be done. It's actually a little more complicated than that because various features of the telescope or the analysis can convolve non-smooth structure into the smooth foregrounds. And then it's not just smooth versus unsmooth, it's unsmooth versus unsmooth, basically. And so we need to know a bit more about what actually is done with these foregrounds in the analysis in order to try and separate them from the cosmic signal. This might sound extremely difficult, and it is difficult, but I'll show you that we've had some success in this endeavor, and there's more on the way. Okay, so this is hard. Well, let's think of something easier to do before we tackle the truly hard problem of just measuring the 21 centimeter emissions from this map, which will be buried under a factor of 10 to the 5 of foregrounds. Well, something slightly easier we can do is we can say, we know that all of the neutral hydrogen gas should be locked inside these galaxies. So if we know where the galaxies are already, then we can look at the same location in our map and verify that we see a bit higher intensity where we know a galaxy is, or see lower intensity where we know there aren't any galaxies. If we were extremely lucky, we could do this by eye, like so, and just look and verify indeed the contours of brightness are mapping where we know the brighter objects are because we've already measured them. In this way, we can measure correlations between the clustering of galaxies and a hydrogen. And this isn't just an easier step on the road to the harder thing. There's actually some physics that we can learn here, both at very large scales and on smaller astrophysical scales based on how this correlation works. And so this is the first thing that we've tried to do in the data. Now, if we look at the data itself, it looks something like this. Here's an example of a sky map made by CHIME at 700 megahertz, which in redshift to 21 centimeter emission corresponds to redshift around 1. And this map was made from around 500 hours or 22 days of integration time. And you can compare this to the total amount of data we've collected so far, which is on the order of 5 years. So this is actually only a small fraction of the data that we have so far. Now, if we look at this map, we don't see any 21 centimeter emission. What we see, oops, skipped ahead. What we see is synchrotron emission from the Milky Way, this diffuse structure, which stretches across the map diagonally. And we see a variety of radio point sources. These are there are different things. One example of these are bright supermassive black holes, which have a lot of material nearby, which is being accreted onto the black hole and spewing out lots of radio emission, which we pick up in our maps. All of these things are interesting in an astrophysical light, but for us, they are contaminants. We wish they weren't there, and so we need to filter them out of our maps in order to get the cosmological signal that we want. Without going into too much detail, we have a procedure that we've settled on for doing this filtering in a first round analysis. So after we apply various filters to the map to try and get rid of all these foregrounds, we've reduced the fluctuations in the map. If you compare the color bars here, we've gone down by a factor of about 3,000 in the RMS fluctuations in the map. What you see in this map now, well, the first thing you see is still some residual systematics of extremely bright sources passing through the beam. In the cleaner regions of the map, what you see now is pure instrumental noise. So we're still not seeing the 21 centimeter signal. We can't do this cross correlation by eye, like in the overlap I showed you. We need to do some statistics to try and extract the cosmological signal from under the noise that you see in this map. So the way that we do this is with a stacking analysis. The way to think of a stacking analysis is to think of the true large-scale structure, which is captured by our map. So in the true universe, there's going to be some distribution of matter, and we have a catalog of galaxies that we've obtained from some other telescope, and these galaxies might sit at the red points. Now, at each angular location of a galaxy, we can try and find the pixel in the CHIME map which contains that galaxy. This will look something like this. So CHIME, like any telescope, it has a finite angular resolution on the sky. So one pixel in our map will correspond to the total contributions of structures near each galaxy if the galaxy is contained in the pixel. This is an interesting point. When we do this stacking, we're not only measuring the emission from the hydrogen in a galaxy, we're measuring the emission from the hydrogen near the galaxy, which is correlated with the galaxy's position by well-known descriptions of cosmic large-scale structure. And so we can go into our map and find each pixel where we know a galaxy is living. And then we can do this for all of the maps that we make. CHIME makes about 1,000 maps which are finely spaced in radio frequency. And so for each map, we can find the angular pixel where we know a galaxy is living, and then arrange all these pixels in a line. Effectively, we're taking a pencil beam, we're measuring a skewer through the universe at an angular position of a galaxy as a function of distance or as a function of observed frequency in our maps. Now we can do this for every galaxy in our catalog. From the catalogs we have, we end up with tens of thousands of galaxies that we can do this with. So we can do this procedure for each galaxy. We can take all of these pencil beams, center them on the line of sight location of each galaxy, and then average them down or stack them. What we expect to see is, on average, at the location of each galaxy, that is at the angular location and at the radial location, we expect to see an excess of emission in our maps. At locations just behind or just in front of each galaxy, we also expect to see, on average, some emission which rises above the noise. And then because of various filtering procedures we get an extra shape convolved into the signal. So this is why you see this scalloped shape instead of a smooth fall off, which we would normally expect from cosmic large-scale structure. And if we look sufficiently far from each galaxy, then we expect the signal to be subsumed into the noise. Okay, so this is what we expect. For the experts in the room, this might seem like a somewhat convoluted way to do a two-point correlation. The more natural thing you might think of doing is a cross-power spectrum, but a cross-power spectrum involves a lot more manipulations of the data. This was the minimally invasive way which we could find to measure a two-point correlation, which we expect to be there. And so this is what we went with in the first analysis. This is the idea of what we've done. And if we look at the results, then here they are. So based on the EBOS galaxy survey, which was carried out by the Sloan telescope, we have catalogs of 3 different classes of galaxies: emission line galaxies, which tend to have fairly active star formation and somewhat lower mass; luminous red galaxies, which are older and have more quiescent star formation; and quasars, which are distant supermassive black holes, which are sending a lot of radiation our way. If we perform this stacking procedure on each one of these catalogs, then we find a significant detection of a signal which rises above the noise at signal to noise around 6, 7, and 11 for each catalog. And so this verifies that indeed our maps do contain the 21 centimeter signal, which can be pulled out of the noise if you do a careful analysis. This represents a milestone in the field of 21 centimeter intensity mapping. It's the first such measurement with a custom-built instrument with an interferometric telescope, as opposed to a single dish telescope, which makes a map 1 pixel at a time, and at redshifts greater than 1.2, which corresponds to times greater than 9 billion years ago. And so here we did it. Unfortunately, what we found from this analysis is that the information about cosmology that we could extract was somewhat limited. It was limited because this is our first detection, and we had to do filtering on the data, which was so aggressive that we actually smoothed out a lot of the information that we were after. And so I'll talk a bit later in the talk about the next steps we'll take to try and ameliorate the situation, pull back some of the interesting signal, and learn some interesting things about cosmology. However, there is still non-zero information content in this measurement, clearly. I'd like to show you a quick piece of what I call ancillary science, something which we didn't set out to measure, but something which fell out naturally from this measurement. So if you look at the stack on the quasar catalog, which was the rightmost panel that I showed previously, if you look at the shape of this profile, you'll find the centroid is not quite lined up on the zero lag bin. Right? You can tell this one is slightly bigger than this one. And so therefore, this peak appears to be slightly shifted to the left here. We discovered this because when we were trying to fit the theory template, which is in red on this plot, to the data, we found that the fit was poor unless we added an extra parameter, which allowed us to shift this theory template to the left or to the right. Once we allowed that parameter, we found that it is actually measured at high significance. Well, high depending on what your standards are. For us, it was high, around 3.3 sigma. And so this is a significant detection that there's a shift in the centroid of the stack. The natural interpretation of this is that there is a systematic bias in the redshifts of the quasars that were reported by the EBOS collaboration. So the EBOS collaboration hands us a catalog of objects. They say, we think they're at this angular location and this line of sight distance. And what we've seen is that the line of sight distance that is reported is actually a little bit different on average from the true line of sight distance to these objects based on their cross correlation with other measurements of large scale structure. Now, the EBOS team on their own did an independent estimate of this bias, and they found a non-zero bias, which is consistent with ours, but we obtained a completely independent measurement of this bias. Physically, what this means is that the emission lines which were used to determine these redshifts of the quasars are systematically blue shifted. These emission lines are mostly measured from gas surrounding these quasars, and there are various outflow mechanisms and other things which cause the systematic blue shift. And there's some understanding of this in the astrophysics literature, but not a complete understanding. And this is something which comes out naturally from our observations. So in future analyses, when we have a much tighter measurement of this offset, we can begin to split the quasar catalog based on different properties, and then feed this information back into our astrophysical knowledge and really learn something about the physics of the gas which is surrounding these quasars compared to the galaxies which are hosting these quasars. Not something we set out to do, but something which comes out, and we expect more of these kind of things to pop up and feed back into other scientific communities as we move forward. However, the real thing we want to measure is the cosmological information, and this is also in progress. Now, there's other types of cross correlations we can do. So I'll touch on another one, which was also recently published this year. Instead of looking at correlations between our sky maps of the 21 centimeter intensity and the positions of galaxies, we can also look at cross correlations with another observable in cosmology called the Lyman alpha forest. The way the Lyman alpha forest works is that if you have some distant quasar, typically you'll measure the spectrum of radiation from this quasar. And then you can look for a giant peak in the spectrum, and this will typically be Lyman alpha emission from the quasar itself. So you can use this to determine the redshift. However, if you look at other regions in the quasar spectrum, quite often you'll see sharp dips happening at certain wavelengths. What happens to generate these dips is that emission from the quasar propagates outward, it gets gradually redshifted, and then if it has redshifted into the wavelength corresponding to the Lyman alpha transition, at a location when it encounters some cloud of neutral hydrogen, then the neutral hydrogen will absorb that photon, and then it won't propagate past. So you'll see a dip in the spectrum. And this is independently measured with high significance now. And if you can do this kind of mapping of all of these suppressed transmissions, you can figure out where all the neutral hydrogen is along the line of sight to each quasar. If you do this for enough quasars, then again, you can start to get a 3D view. However, what we know is that this Lyman alpha forest, this independent measurement, is telling you where all the clumps of neutral hydrogen are. Our maps, once we filter them correctly, they're also telling you where clumps of neutral hydrogen are, because we're getting 21 centimeter emission from these clumps. And so if you try and correlate the locations of these dips with our map, we expect an anti-correlation. Wherever the flux goes down here, we expect the intensity to go up in our map. And so if we run the same kind of stacking procedure that we ran for the galaxy and quasar catalogs, we can try to measure this correlation, anti-correlation, and indeed, we have measured it at around 9 sigma. So this analysis was led by, at the time, a graduate student at the University of British Columbia, Tristan Pinsonneau-Marotte, and he's since moved on to a postdoctoral position on other topics, but he still maintains ties with CHIME and 21 centimeter intensity mapping. So this was also the first time this kind of correlation has been measured at a mean redshift of 2.3. So this surpasses the previous record for the highest redshift 21 centimeter emission ever measured, which was also set by CHIME. And again, the cosmological interpretation of this signal is a little difficult, not only because of the filtering we've done, but also because of the story of the astrophysics of these objects. The clumps of neutral hydrogen in the Lamanalpha forest tend to be low density regions, not quite located where the galaxies are. The hydrogen we're measuring in the maps tends to be high density regions, more closely associated with galaxies. And so it's not true that we're actually measuring the same clumps of hydrogen when we do this cross correlation. We're measuring an extra correlation between the high density clumps of hydrogen and the low density clumps of hydrogen. This is a modeling challenge, but also an opportunity to actually learn about this cross correlation and again, feed it back into the astrophysics community to learn more about how these clumps of hydrogen are behaving and correlating at different densities. Okay, so this is where we are so far, or the things that we've published so far in terms of cosmology with CHIME. So in the last few minutes, I'll just briefly flash a few things about where we're going next. So here is a plot which is useful for framing the roadmap in the near future. This feature was intended for cosmology experts, but I can still guide you through what it's showing. On the x-axis here is a line, transverse wave number. It is a Fourier mode transverse to the line of sight. On the y-axis is a Fourier mode along the line of sight. So as we move to the right in this plot, we're moving to small angular scales. As we move to the top of the plot, we're moving to small spectral scales or small distance scales along the line of sight. These boxes are telling us the rough ranges of scales that we have probed with these first analyses. So it's telling us in what regime we have learned about the clustering of neutral hydrogen by these analyses. There are different boxes here because the properties of the telescope and the frequency redshift mapping depend on frequency. And so depending on what regime you're looking at, you get slightly different sensitivity in ranges of scales. In the bottom left of the plot, these three lines correspond to the so-called baryon acoustic oscillation signal. This is the signal that we're actually after to learn about direct energy. And so without knowing too much about what these lines represent, you can still see that these lines are falling outside of the range of sensitivity that we had for our first analyses. And again, this is because of basically data quality issues in early stages in these analyses. We had to do fairly severe spatial and spectral filtering in order to remove all the foregrounds and contaminants. And it turned out that this cut off our sensitivity to the thing that we originally wanted to measure. And so we have our work cut out for us in the next few years. What we need to do is try and improve our analysis procedures and systematics mitigation in order to decrease the severity of our filtering and push these sensitivity ranges all the way down, such that we can get back to the regime where we can learn about dark energy. But at the same time, there's still a lot of useful information that we can obtain from these other scales. And so we're working on refining our cross-correlation analyses to try and pull more of this information out. Okay, so in the last few minutes, I'm going to do a rapid-fire overview of some of the things that are currently going at ASU and within CHIME. One of the things that we need to do is try and enumerate small systematic effects in our analysis which might affect what we're measuring and try and remove them. One of the more interesting ones is expansion of the focal line. Here are the antennas that CHIME uses to measure radio waves from the sky. They're hung upside down from aluminum cassettes, and these cassettes are themselves hung from a steel focal line. What we know about metal in general is that it shrinks and grows as the temperature changes. And so as we make observations throughout the day and night, or as we make observations through different calendar seasons, the distances between these antennas change slightly in a time-dependent way. And this affects how we interpret the maps that we're making and what we're measuring. And this can be as much as a few percent effect on the data, depending on the precise regime you're looking at, which can be large for the type of analysis we want to do. So I'm working with an undergraduate student here at ASU, Grace Connolly, to try and perform a new simulation of this focal line expansion effect so that we can quantify precisely the impact it has and then test out some mitigation strategies for removing it, of which we have a few ideas. So here is a rough plot from Grace, which shows the ratio of data simulated, including this effect or not. And you can see that we're reaching a few percent level impact on this data. And so this is really critical that we understand what this is doing and how we can remove it. We can also think about different ways to do cross-correlation analyses. The analysis I described to you was a purely one-dimensional analysis. That is, we only looked at the profile along the radial direction, but we can also ask about angular correlation information. This was already partially done in the paper which published the initial result, but there was not any attempt to really go deeper than this plot, essentially, no attempt to extract information from this plot, because this is a difficult endeavor. But with a postdoc here at ASU Alban, we're working on new ways to try and perform this kind of 2D cross-correlation analysis and interpret it, and also apply this analysis to a cross-correlation with damped Lyman alpha absorber systems, which are extremely dense clumps of neutral hydrogen, which have been measured separately, and which should also have a high cross-correlation signal. Now, also within the CHIME collaboration, one of the key things that we're moving towards is the autocorrelation of 21 centimeter intensity, not using any external data, just using CHIME data on its own to measure these fluctuations. This would be a key step in the entire field of intensity mapping. There's only been one claimed detection of an autocorrelation thus far by another telescope project. And so we want to rapidly move towards this with CHIME and begin to characterize how we do this analysis so that we can eventually use it for cosmology. These efforts within CHIME are being led by a postdoc at McGill University, Arnab Chakraborty. And here's a rough plot from Arnab comparing some filtered data to a realization of the expected noise. The take-home message from this plot is that we are able to filter the data so that the foregrounds are suppressed to at least the level of the thermal noise in the data. And this is already a success for us. And then what we can do from this step is apply some more statistics to this plot in order to average away more of the noise and dig down into the signal we want. This work is ongoing, but we're making good progress. One final point I wanted to make is we've been working a lot on CHIME, but maybe we should build another telescope to do even better. CHIME itself will be running through at least 2029. So there's the potential to modify how we're taking data if we see fit to do so. But in parallel, there's a sibling experiment called CHORD, which is currently being built right next door to CHIME, and which will use a lot of the same infrastructure. CHORD has a different design in order to have better control of systematics and beam measurements. Will be made up of around 500 radio dishes, and will have 3 times higher sensitivity and measure twice the cosmic volume as CHIME. So we expect to make bigger maps and pull a lot more information out of these maps. We're rapidly moving toward CHORD. There will be a 64-dish Pathfinder experiment, which will be finished by the end of this year. That is metal on the ground. And by early 2026, we expect to have all 512 dishes in place. And there's a PhD student here at ASU, Panos, who is helping perform some simulations of the CHORD Pathfinder in order to start testing the analysis and seeing how much early science we can get even out of this small initial chunk of the full CHORD array. And so this is a bit of a snapshot of where we're going soon. And this is all I wanted to tell you. So let me quickly summarize and by saying that there's still a lot of open problems in cosmology, the nature of the early universe, the nature of the late accelerating universe, and dark matter, which is everywhere in between. We can try and probe some of these mysteries by looking at large-scale structure. 21 centimeter intensity mapping provides a promising way to do so. The CHIME telescope has made its first measurements, and there's many more to come. And then there's a sister experiment, which is rapidly ramping up and will give us a lot more information. So in general, there's a lot of scientific promise here, but there's still a lot of work to do. So I encourage you to stay tuned for the things which will continue to happen within the next few years. All right, thanks.